Okay, so version 7.1 of the Tycho software has just now been released, and one of the key enhancements with this update is that it offers a much improved integration of orbital elements. So what that means is that it can now compute to a much greater degree of precision the expected position of objects within the field of view. So the way this works is that it conducts a two-pass operation. In the first pass, it solves the Kepler formula to determine which objects are within the field of view, and in that process it then computes the approximate position of those objects. And that is essentially how the old version would operate. It would take the orbital elements of all known objects and determine which of those objects then exist within the field of view, and that would arrive at an approximate position. But now, with this update, we take it a step further, and we then submit those objects that have been identified as being within or close to the field of view, and we submit them to a modified version of the Find Orb software, which in turn will then compute and solve for a much more precise position of those objects. And it will also convert from geocentric to topocentric coordinates, again in the interest of achieving 1 arcsecond or better precision. In addition to that, this update now also supports the orbits of comets as well as other custom objects of your choosing. So here's a screen capture of the updated known object database window, and as before you can download the MPC orb database file which contains the orbital elements of known asteroids, but now you can also download the comet database file as well as specify a path to a file containing orbital elements of custom objects. So with that, let's go ahead and take a look at a demonstration. Okay, so in this first example, I'm going to take a look at the data set that's provided as an example. You can follow along with it in the user guide. So it's a fairly common data set to work with. So if we go to the image viewer, it's going to load up all the images, and what we can do is go to File, Load Known Objects. So what's going to do here when I do that is it pops up a new window, and it just submitted all the eligible objects to Find Orb, and it has already returned back with a response. So these are all of the objects within the field of view. So for example, if I click on one, then as you can see, I can zoom in, and you can see we have very good position of that expected object. So I can do that for other objects as well. So when you click on them, it simply goes to them, even if they're not quite visible. So we have magnitude information in this column. We also have the distance to the object in astronomical units. So it's very easy to use, and you can also, for example, here is a near-Earth asteroid. So as you can see, we've converted to topocentric coordinates. So in this stack here, we've resolved that object very well. If I were to change my observatory location, let's suppose I were then at W94, then if I run it again, then of course those coordinates will not be as precise. So if I go back to this object here, then it now looks like a smear. The speed is now 1.8 arcseconds per minute, whereas it was 2.05 before. So even though the position is approximately correct, the stacking is not as accurate. So this enhancement, we now have, again, not just accurate position of objects, but also their speed and position angle. And so that's very nice. So I can go back here to fit the correct observatory. And then again, we can look at that example one more time. So again, here's the object, and has the proper speed. So this is very nice to have that. If I were to disable that option, so if you wanted to go back to the old version and disable computation of precise position, then I can show you what that looks like here. So first of all, that near the object is not even identified in the field of view, but the other objects, so this is where the object actually is, and it thought it was here. So that is how much off the position is. And that is owe in large part to how different the timestamp of the images are compared to the epoch of the orbital elements. So if you were to load an orbital element file that was taken very close in time to when the images were acquired, then they would be much more close in proximity. But these were acquired in 2018. These images were acquired in 2018, whereas the orbital elements here were computed in 2020. So that's where the integration of orbital elements, you want to have that account for perturbations and so forth. And so I go back here and check that option, and now we can recompute their positions, and again you can see that that asteroid is indeed right here. So that is the expected position. So again, it's very easy to use. You can also sort columns. So if I wanted to sort by brightness, I can do that. So here's magnitude. So as you go fainter magnitude, then you expect it to be fainter here and so forth, and it is. So here, that's magnitude 20.9 and so forth. And so they make out a mag 22.3 in this data set. Anyway, so it's now very easy to use, and these precise positions are very useful, not just for this known object window here, but also here in the next example. Okay, so in this example, what we want to do is we have identified a set of tracks. In other words, we've run the synthetic tracker and it has come back with a set of detections of asteroids. And what we want to do is we want to identify which of these tracks match up with known asteroids. So each of these tracks here could be a new object, a new discovery, or it could be simply a detection of an already known asteroid. So what you want to do is go to File, Load Known Objects, and that's very similar to what you saw with the image viewer. For example, you can do the same thing with the image viewer, but the behavior is different. So if you do it from the image viewer, it loads up the known object window, but if you do it from the track navigator, then it compares these tracks with the known objects. So as you can see here, it has come back with the results, and it has identified, for example, this first track is 2000 RZ92. The next one after that is 1999 TH90. And then here's our near-Earth object 2018 RB. So I can double click on that and you get the animation. So it has correctly identified these tracks with known objects. Even though the images were taken 2 years ago, it has computed the more precise position of these objects according to the orbital elements. And so the old version, if you were to examine the object distance column, which is in arc minutes, the old version, it was not uncommon for it to be 0.3, 0.4 arc minutes, and sometimes much greater, again depending on how out of sync the epoch of orbital elements were to the time that the images were acquired. But now, even though they're 2 years apart from when the images were acquired to the orbital elements, we still have 0.02, 0.04, and so forth as the distance from the expected position of the object. So it's much more precise, and this allows for it to much more correctly identify the tracks with known objects. Okay, in this next example, I mentioned that we now have also the ability to support comet orbits as well. So here's an example of a data set that contains a comet. So as before, we can load up known objects within this field of view, and one of the objects happens to be Comet 2017 B3. So when I click on it, you can see that it has correctly computed the position of that object, and it is indeed a comet. So again, this works very well for asteroids, comets, even for custom objects where you have computed their orbital elements, it will work for those as well. Okay, so that wraps it up for this video. Thanks for watching. See you next time.